Enterprises need AI to parse massive document libraries, but relying on standard cloud-based language models creates a critical vulnerability. Sending proprietary files off-site through open APIs exposes sensitive information to external network risks. From a legal and operational standpoint, pushing internal data through zero-control cloud processors breaks strict compliance protocols. Once the data leaves the local network, you lose sovereignty over how it is processed or retained. To eliminate this risk, the architecture has to pivot. The AI generation engine must be completely decoupled from the open internet. This is DocuSense AI. As we can see on this interface, the system is a 100% locally executed retrieval augmented generation or RAG system. The URL bar confirms it is running securely on localhost port 8501, utilizing a local Llama 3.2 engine. This localized stack operates on three distinct pillars. Llama 3.2 handles the generative text, Ollama manages the local orchestration, and ChromaDB securely stores data on premises. While the backend is dense, the system presents to the end user as a streamlined, state-persistent front-end built with Streamlit. By combining offline orchestration with open-weight models, developers can deliver enterprise-grade generative capabilities while maintaining absolute zero-trust data compliance. Looking at this architecture diagram, the process begins in the Phase 1 document ingestion quadrant. PDF algorithms extract the raw text. Large language models operate under strict memory constraints known as a context window. Feeding an entire 50-page contract directly into the model will overwhelm this window, causing the system to fail. To bypass this limitation, the system uses chunking, dividing raw text into distinct blocks. The text splitter enforces a limit of 1,000 characters per block. To prevent ruining context, the pipeline uses a 100-character chunk overlap. This overlap is mandatory. Sharing trailing characters of one chunk with leading characters of the next prevents semantic destruction, ensuring core concepts stay intact. Structuring the text with rigorous overlapping chunking is the absolute prerequisite for achieving high-fidelity data retrieval later in the process. Once the text is chunked, it must be translated. Databases cannot natively calculate the relationship between English paragraphs. They require mathematical values. The system runs each block through the nomic embed text model. This process, vectorization, converts raw text into multidimensional numerical arrays representing actual semantic meaning. Chunks discussing similar concepts naturally map to coordinates closely clustered together in physical space. The system then stores these spatial coordinates inside ChromaDB, a highly specialized, locally hosted vector database. The pipeline passes the prompt through the embedding model, creating a query vector. Semantic search is a geometry problem. The database calculates the shortest mathematical distance, MIT vectors, to find relevant data. Traditional keyword matching fails if the exact vocabulary doesn't match. Vector distance bypasses this by measuring intent, pulling the right data regardless. By treating language as spatial data, vector databases replace fragile keyword matching with robust intent-based alignment. With the relevant data isolated, LangChain acts as the orchestration layer, connecting the vector database directly to the Llama 3.2 execution engine. DocuSense employs a retrieval QA pipeline using a stuff chain architecture. LangChain grabs those mathematically relevant chunks and physically stuffs them into the prompt, right alongside the user's original question. Llama 3.2 processes this augmented prompt, instructed to generate its final response constrained purely by the injected paragraphs. Let's look at the pipeline executing in real time. This interface displays the system processing a complex query about university admission procedures. The AI returns a precise breakdown. The output maps exactly to the injected vector data, proving the stuff chain's execution by correctly pulling highly granular terms like VITEE score and counseling. The critical test for any AI deployment is how it handles a lack of information. Standard models often hallucinate facts when queried on missing data. Here, the user requests PhD eligibility constraints, data not present in the ingested file. The model responds precisely, "I don't have the specific information." Because ChromaDB found no vectors detailing PhD requirements, the LangChain constraints worked as designed. The model correctly identified an absence of data, rather than inventing a plausible-sounding lie. When exact text chunking pairs with tight orchestration constraints, local RAG neutralizes the hallucination problem for enterprise applications. Comparing standard cloud AI routing to the DocuSense architecture, the structural advantage is immediately clear. Text chunking, ChromaDB vectorization, and Llama 3.2 generation all execute strictly on premises. Because the isolated data loop is fully closed on premises, the operational risk of external data leaks drops to zero. This secure containment makes the system highly viable for industries managing sensitive intelligence, sensitive medical histories, or proprietary engineering blueprints. And because the Streamlit front-end masks the mathematical complexity of the vectors and orchestration, non-technical corporate staff can safely interrogate the database right from their browsers. Executing local orchestration requires a highly specific engineering skill set. This system was built by developer Vijay Rajesh R., based in Tamil Nadu, India. The project relies heavily on his core technical competencies in generative AI, LLM optimization, AWS cloud infrastructure, and active open source contribution. This build is backed by a broad base of practical experience, spanning complex generative AI workflows, computational logic in MATLAB, as well as relational data management using MySQL databases. Currently pursuing his BTech in AI and machine learning at VIT Bhopal and serving as a student ambassador at Coincent.ai, Vijay is known for rapid execution and delivering high-efficiency AI solutions. You can review the repository for this project and connect with him on LinkedIn using the links below.